Welcome to my presentation about matching persistent scatterer clusters to building in a mesh representation. My name is Philipp Schneider and I'm with the Institute for Photogrammetry of the University of Stuttgart in Germany. To put this presentation in context, I want to zoom out a little bit and have a greater look on the goal of this research. We are aiming for a citywide per building deformation monitoring and automatic risk assignment based on synthetic aperture radar satellite measurements. And this is enabled by the wide availability of high-resolution SAR data and 3D city models. In the following, I want to present a method that brings together SAR and deformation measurements, namely clusters of persistent scatterers and 3D presentations of buildings. I will shortly present the persistent scatterer method and an approach how to find clusters in such PSI points. In the main part, I will talk about how to link such clusters to building parts and show the method applied to an exemplary building. And in the end, I will present an exemplary web interface that helps to explore the results. So PSI is a differential synthetic aperture radar technique. By comparing the phase of a stack of SAR images relative to a master image, small movements can be detected. This algorithm searches for scatterers with a phase change over time that fits to a deformation model. And this works especially well for build-up areas, since metal objects and buildings act as good reflectors. And the main product of PSI is a 3D point cloud and the deformation history for each point. Here we see a PSI point cloud overlaid with a 3D city model. And we see that the PSI points occur on buildings but are not present in vegetated areas or areas that undergo rapid changes, like this construction site here or this park. The interesting thing about this method is that we receive a time series for each point that gives us the deformation history with millimeter accuracy. So how do we find groups or clusters in such a point cloud? For future considerations, let's look at this two-dimensional example here. Here are some PS points scattered on a simple building. And for each PS point, we also have a time series. And we can now treat these time series as points in a three-dimensional deformation space, with here one dimension per deformation date. And this is a very simple example with only 3 dates, but there are actually dozens of these dates, so also dozens of dimensions, so one per SAR image. You can already see those clusters forming here, right? And the assumption is that these clusters show a correlated deformation behavior because they lay on the same rigid structure, for example, here on the roof or on the facade of the building. And now we want to link those clusters to a segmented mesh that represents different segments of the building, maybe coming from a city model or a building information model. So this exemplary model has 4 segments: the chimney, the roof, and 2 floors. Each of the segments is represented by a submesh built up from vertices and edges. We are now looking for the optimal assignment so that each of the 4 segments is associated with one of the 2 clusters. We used a modified Hungarian algorithm for this. And as the qualification matrix Q, we use 1 minus the normalized vertex neighbor count. And I show you what I mean with that in a second. So for each vertex in the match, we count the class appearance in the k closest PS points. So that means the k closest points. Here we use actually 3, but in the publication we use 10. So for each vertex, let's start with this vertex here, we count the 3 closest neighbors, so this is these 3 points. So cluster 2, the blue cluster, appears 2 times and the red cluster appears once. So 2, and 1. And then we add to that the 3 closest neighbors for this vertex, so 3 and 0 for the red cluster, and for this vertex 3 and 0 for the red cluster, and 3 for this one as well. So in total it is 11 for the blue cluster and 1 for the red cluster. And we can do that now for the next segment. Here it is 6 and 3, and for the rest it is 4, 8, and 1 and 11. Each column is now normalized, so all segments get the same weight regardless from the vertex count. And we concatenate the matrix so each cluster can be assigned to multiple segments. So we just put here the same matrix a second time underneath. And now the Hungarian algorithm gives us the optimal one cluster to many segments assignment. So segment 1 is assigned to the blue cluster, segment 2 is assigned here to the blue cluster as well, segment 3 is assigned to the red cluster, and segment 4 is assigned to the red cluster as well. As a quality metric that gives us a grasp of how well the mesh segments represent the borders of the cluster, we use the per segment entropy, so basically the entropy for each of the columns here in this matrix. And the high entropy value hereby means that the cluster to the segment allocation is not very clear. So this was our pipeline, and we want to apply this now to an actual site. So the requirements for this is that we need to have obviously high resolution SAR data, and we also need a 3D model or a BIM model that we can use for the analysis. And preferably there should be some deformations going on. So as a study object, we choose a very prominent building in Berlin, Germany, where a mesh is available. This model is based on a very detailed mesh, and the mesh is segmented into reasonable subparts, like here these turrets and these columns and parts of the cupola. For the SAR data, we use TerraSAR X data with a resolution of approximately 1 by 1 meter. The 89 images were taken in a time span of approximately 3 years. And we use SARscape 5.5 with a linear deformation model for the PSI processing. And we could extract more than 10,000 PS points on this building here. For the future analysis, we only use the PS points with a model coherence of better than 0.7. So that means they fit very well to the chosen deformation model. You can see that the estimated position of these points concurs very well with the 3D model. We used the previously described clustering pipeline to come up with segments of the building that show a correlated deformation behavior. We then used the optimal assignment to fuse the mesh and its segments with the PS point clusters. This assignment worked very well on parts like the base, the towers, and the cupola. But here from this entropy plot, you can see that some parts, like here this gate, do not correspond with the cluster structure. We also created a web tool where you can explore the here presented examples in 3D. We also present the results for this pipeline on a second building. I think a web tool is very important to present such an analysis to decision makers or civil engineers. That brings us to the conclusion. We presented an approach to link PS clusters to structures in a mesh. We evaluated our method on 2 exemplary buildings and presented a web tool that helps to understand and interact with the results. For future work, we are using an actual BIM model in the real world to help with the integration of satellite-based deformation monitoring in such an environment. Thank you for your attention.